Organic chemistry can feel like trying to learn a whole new language, right? One with all its own secret rules and grammar. But what if I told you that all those super complex reactions are actually governed by just a few basic principles? In this explainer, we're going to decode that molecular language. We're going to find the hidden logic that decides how and why molecules do what they do.
So, what are these unseen forces really? What is it that's constantly pushing and pulling electrons around, deciding which bonds are going to break and which new ones are going to form? And that, right there, is the big question we're here to answer.
So, here is the game plan. We'll kick things off with how a reaction even gets started. Then we'll dive into this incredible unseen dance of the electrons. We'll figure out how to rank their influence, how to predict which molecules are stable, and finally, use all that knowledge to tackle the big concepts of acidity and basicity. First up, how does the whole show begin? Every single organic reaction, I don't care how complicated it looks, it all starts with one simple event. A chemical bond breaks. And how it breaks, well, that sets the stage for everything that comes next. See, when a bond breaks, it can go one of two ways. In what we call heterolytic cleavage, one atom gets really greedy. It just takes both of the shared electrons for itself, becoming negatively charged, and leaving its partner with a positive charge. But in homolytic cleavage, it's a much fairer split. Each atom takes one electron, and they go their separate ways. They're neutral, but believe me, they are highly reactive. This whole bond-breaking drama creates what we call reaction intermediates. These guys are the short-lived, super unstable middlemen of any reaction. You've got the electron-poor carbocation, the electron-rich carbanion, and the neutral but very edgy free radical. Getting a handle on these three is absolutely crucial for understanding everything else. So here's the cool part. Even before a reaction kicks off, there's a constant, invisible push and pull of electrons happening right inside the molecule. These permanent shifts in electron density are called displacement effects, and honestly, they're the real puppet masters of chemical reactivity. First up, we've got the inductive effect. This all happens in those strong, stable single bonds. Yeah, chemists call them sigma bonds. The best way to think about it is like a molecular tug of war. If one atom is more electronegative, it just pulls the shared electrons a little bit closer to itself. It's not a complete transfer, just a permanent little tug, which makes it a weak but always present force. Let's look at 1-chloropropane for a second. That chlorine atom, it's super electronegative, so it yanks the electrons from the first carbon, giving that carbon a slight positive charge. Now, that carbon feels a bit electron deficient, so it starts pulling on the electrons of the second carbon, which then, you guessed it, pulls on the third. It's like a chain reaction of electron tugging. But here's the catch. This effect doesn't last. It's got a really short reach. The first carbon feels the pull the most, the second feels it a little less, and by the time you get to the third carbon, the effect is barely even there. After about 3 or 4 bonds, it pretty much fades away to nothing. Okay, next up is hyperconjugation, and this one's a little weird. It's where electrons from a nearby single bond can kind of jump over to help out an empty spot, like you'd find in a carbocation or a free radical. It's almost like a temporary loan of electrons, which is how it got the awesome nickname, no bond resonance. And finally, we have the heavyweight champion of them all, the mesomeric effect, which you probably know better as resonance. Now, this doesn't mess with single bonds. This is all about the more mobile pi electrons that you find in double bonds and lone pairs. And this effect isn't just a small shift, it's a complete delocalization, spreading a charge over multiple atoms, which is an incredibly powerful way to stabilize a molecule. Now, molecules are complicated, and a lot of the time, these effects are all happening at once, kind of fighting for control. So how in the world do we know which one wins? Well, for that, we need to know the power ranking. And here's the pecking order. Resonance is almost always the king of the hill. That complete movement of pi electrons just makes it so powerful. Hyperconjugation slides into second place, and the weak little tug of the inductive effect comes in last. But there is one massive exception you have got to remember, the halogens. Their electron withdrawing inductive effect is just so strong that it actually beats out their electron donating resonance effect. It's a special case. Okay, so we've got the effects, we know who's strongest. So what? Why does any of this matter? Well, because now we can use all this to predict the stability of those reaction intermediates we met earlier. This is really where it all comes together. The logic here is actually super simple. Carbocations and free radicals, they're electron poor. They are desperate for electrons. So of course, any group that donates electrons, the ones with positive effects like plus M, plus H, and plus I, is going to make them more stable. And on the flip side, you have carbon ions. They're electron rich. They have too many. So groups that withdraw electrons, those with negative effects like minus M and minus I, help pull that extra charge away and make them way more stable. And if you need a dead simple way to remember all this, just think, like stabilizes like. Positive intermediates, the ones that are poor in electrons, are stabilized by positive electron donating effects. And negative intermediates, the electron-rich ones, are stabilized by negative electron withdrawing effects. It's as simple as that. All right, time for the grand finale. Let's take everything we've learned, bond breaking, all those electronic effects, the stability rules, and use it to solve one of the biggest puzzles in organic chemistry, figuring out which acid or base is stronger. Comparing acids might seem intimidating, but trust me, there's a foolproof 3-step plan for this. Step 1, just pluck off the acidic proton, the H+. Step 2, take a good look at what's left behind. That's the negatively charged conjugate base. And step 3, use our rules to figure out how stable that base is. And here's the golden rule, the most important part. The more stable the conjugate base is, the stronger the original acid was. Period. So why does that work? Well, think about it. A molecule is totally fine with giving away its proton if the thing it becomes is stable and can handle that new negative charge. So anything that can pull that negative charge away and spread it out, like our electron-withdrawing friends, the minus M and minus I effects, is going to stabilize that conjugate base, which in turn makes the original acid way stronger. Now, basicity is basically the other side of the same coin. It's not about giving up a proton, it's all about how eager a molecule is to use its own lone pair of electrons to go out and grab one. So what makes a base strong? Well, it needs a pair of electrons that are just sitting there, ready to go, super available. So naturally, electron-donating groups, plus M and plus I, push more electron density right onto that atom, making it way more eager to share. On the other hand, anything that pulls those electrons away, like electron-withdrawing groups or resonance that spreads them out, makes them less available, and that weakens the base. We started out asking about these unseen forces that run the show, and now we know them. The inductive, hyperconjugation, and mesomeric effects. We've seen how they control the stability of intermediates and how they dictate the strength of acids and bases, which leaves us with one last thought. Now that we have the keys to the kingdom, you have to wonder, what other secrets of the molecular world can we unlock?